The first transformer over there, built by British scientist Michael Faraday in the 1830s, is remarkably similar to devices we use today. Although he understood electromagnetic induction, he didn't really get to use his new device. He never tried changing the number of turns, for example, which is when this becomes really useful. That's what we're going to do in this lesson. This slide shows what Faraday was experimenting with. There are two coils wrapped around an iron core. Faraday saw that when the switch closes in the primary coil on the left here, so electricity starts to flow through it, the galvanometer attached to the secondary coil recorded a voltage momentarily. When he opened the switch, it recorded a voltage in the opposite direction, momentarily. Here it is on a loop. Note that the voltage would not last this long. I just slowed it down so you could see it. We should try to understand what is happening, so let's go back to just watching the switch close. To simplify this, the animation is only showing the currents when the switch closes. Now, the left coil is the primary coil, the first one. It has a battery, so it is driving a current. The current creates a magnetic field, and we just need to use the right-hand grip rule for that. See that I've indicated we get a north pole on the right-hand side. But if you pay attention, you should realize that when we close the switch, we are going from having no pole at the right to having a north pole at the right. Why is that important? Well, we are inducing an EMF in the secondary coil, and Lenz's law tells us the induced EMF will oppose the change producing it. Creating that north pole is inducing the EMF. So it wants to destroy that north pole. It will do that by creating a south pole at that end. We're trying to make a north pole, so the EMF will try to cancel it out. To make a south pole at that end, we can use the right-hand grip rule to show we need a current going up at the front and down at the back, opposite to the current in the primary coil. Watch it again a couple of times to see that. Here's the switch opening. See how the induced current is opposite to the primary coil current. I'll let it run a few times. Okay, so now I'm looping through the whole thing again. How could we increase the voltage in the second coil? Do you remember Faraday's law for electromagnetic induction? How can we increase the voltage? Well, Faraday's law basically says that the induced EMF is proportional to the rate of change of the magnetic field in the coil. But remember that one way to do this was to increase the number of turns in the coil. Increasing the number of turns in the coil will increase the change in magnetic field linked to the coil, so the EMF will be larger. Put more simply, more turns, more voltage. Here's the equation showing how the ratio of the voltage in the primary to secondary coils is equal to the ratio of the number of turns. It also states that Vp over Vs equals Is over Ip. Anyway, let's rearrange that. So Vp Ip equals Vs Is. V times I, is that familiar? Power equals VI. We are saying that the power in the primary coil is equal to the power in the secondary coil. That's good because it means conservation of energy is still okay, and we don't like breaking the laws of physics, do we? Here's a circuit diagram for a transformer with the power supply, the transformer, and the secondary load, which would be our voltmeter normally. And this is what a real transformer might look like, with its power supply, transformer, and secondary load. The transformer has a soft iron core that is a loop so that the magnetic field stays inside the iron. It has to be soft iron, magnetically soft iron rather than steel, that is, so that the alternating current can create an alternating field easily. We want to be able to create the field, destroy it, create it, destroy it, so we need a magnetically soft material. But why? Why is it an alternating current? I was using a battery before, wasn't I? That seemed to work. Have a think, what was the problem with my earlier design? Well, I had to keep turning it on and off. I had to keep switching it because the EMF is induced by a changing field. Alternating current is always changing, so the field it produces is always changing. Okay, let's finish this off with some maths. This transformer has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 turns on the primary coil and 1, 2, 3, 4, 5, 6, 7 turns on the secondary coil. Okay. 16 turns on the primary, 7 turns on the secondary. If it has a primary voltage of 240 volts, what will the secondary voltage be? Have a go. First, write the equation. If you didn't do that, write the equation. Remember, an equation has an equal sign. Okay, then rearrange to make what you want the subject to be. So Vs equals Vp Ns over Np. Then substitute in the known values. Put it in the calculator and write the answer to three significant figures, 105 volts. Nothing too tricky there really, but you do need to make sure you get the equation the right way round. This one's called a step-down transformer because the voltage is stepped down from a high value to a low one. If we did it the other way round with more turns on the secondary coil, it would be a step-up transformer. And that's transformers. There was a lot of information there, so use the videos on generators and electromagnetic induction and reviewing this one again to help you to understand it. In the next video, we're going to get to the final part here, which is to understand why we want to use them and why transformers are possibly the single most important machine in your life today.